problems. Am I right? That's true. That's all right.
Yes, sir.
Okay. And do you have any questions about that?
Can you solve again the second problem? Just briefly to remind us of what we have studied last week.
Sure, definitely. That is, yeah, I can do that. For the hypothesis testing, you need to perform the X0 and H1. Okay, you need to perform X0 and H1. So you get you have X0, H1 in this case is that, and for the first problem, M is less than 7.7. For the second problem, H1 is that M is not equals to 105. And then in the first case, you need to find the value of Z, all right, which is 7.5 minus 7.7 divided by the population standard deviation 0.5 divided by the square root of n, and in this case is 50. Okay. And then for the second problem, you can say that you want to find t, and then that's going to be 108.6 minus 105 divided by excuse me. And this the sample standard deviation is 6.3 divided by the square root of n, and in this case is 20. Understand? For the first one, you get you need to use the standard norm distribution, and that is the left tail. So this becomes 5%, 0.05, and this point. What is this point, by the way? This point is minus 1.64. For this, it is the two tails. We have two tails here, and its tail. What is its tail? They are using the t-distribution table with degree of freedom 19, and you can determine this point. Understand what I'm saying? Is this all right, everybody? And then based on that, you can make the conclusions. Is that all clear? Oh, I think I need to record the meeting.
Yes. Why in the second problem we use the t-distribution?
The reason is that in the first case, you have the normal distribution with the population standard deviation. Even though I didn't mention that it is the population standard deviation, it must be the population distribution because we are talking about the population. The population has normal distribution with the standard deviation. So this standard deviation must be the population distribution, the population standard deviation. On the other hand, in the second problem, you get the standard deviation, but it comes from the sample. That's why it is the sample standard deviation, and that's why you need to use the t-distribution. Do you understand?
Yes, thank you, sir.
Okay, is that a question so far, everybody? Is this all clear? Is this all right, everybody? May I move on?
Yes, sir.
All right. Okay, so I want to move. I want to move to the third case. What is that? The third case is going to be when all the xi are independent, but in this case you don't know the distribution. For the first two cases, we do know that the distribution is normal. Okay, you can see that you have all these assumptions. You have the assumption of normality. However, in the third case, we don't have that assumption. In fact, we do know that they have the same mean values. Yeah, they have the same variance values, but the distribution is not normal. And if the distribution is not normal, you cannot use the distribution. You cannot use what we have here. The distribution of x minus m over sigma over the square root of n follow the standard norm distribution, or x bar minus m over s over the square root of n. That's follow the standard distribution. You don't know that. You don't know these things. You don't know the distribution of these fractions. So in order to perform the test, you need to know the distribution of x bar. We do not know it. So we need an extra assumption that n is big enough. Okay? Is this all right? Is this okay?
Yes, sir.
Okay. And then we get s bar minus n over sigma over the square root of n. Approximately follow the standard distribution when n is big enough. All right, so you remember that is the central limit theorem. Okay, you can also replace sigma by s to get a similar result as over the square root of n. That approximately follow the standard distribution. Okay, when n is big enough. Is that all clear? That's clear.
Yes, teachers.
Okay. So we can use these results to perform the test as we did before. For sure, it is not the exact test. It is just an approximate test. Okay. So let's go. Let's move on with the following results. Let's consider this example. Spectrometer dissipate is used for measuring material resistance to penetration as a cone is driven into pavement or subgrade. Suppose that for a particular application, it is required that the true density value for a certain type of pavement be less than 30. The pavement will not be used unless there is conclusive evidence that the specification has been met. State and test the appropriate hypothesis using the following data. What do you think about that? All these data set, all the observations, and you draw the histogram, you can see that the distribution is heavily skewed, right? It is not normal, obviously. So you cannot use the exact test, the exact t-test. No, you don't have it. Instead of using the exact t-test, you can use the approximate z-test by using the central limit theorem. We need the assumption that n is large. In this case, n is 52, and you can consider that as a big number. So you can have the h1, which is m is less than 30. So that is what you need. You want to test, okay? And then you want to compute the value z, which is the h bar minus 30, the right hand side of the inequality, over the standard error. The standard error, in fact, it is the estimated standard error, which is s over the square root of n, right? The average value can be computed. Understand? It is basically 28.76 minus 30 divided by the value of s. The value of s is 12.2647 divided by the square root of 52, and then you get a number which is minus 0.73. Okay, and you are using the standard number distribution. In this case, you have the left tail, so you have a look at that. You get the left tail, and the value of alpha is 5%. You get 5% here, and it is minus 1.64. Okay, the rejection region is here, right? And the value you unfortunately the value you obtain z belongs to the rejection region, so we fail to reject the null hypothesis. So the answer is we fail to reject the null hypothesis. Do you understand? That's all clear? It is all right, everybody?
Can you repeat it one again? Yeah.
Sure. You mean from the beginning or which one?
No. Just from the calculation of the z value.
Okay, so z is simply h bar minus 30 over s over the square root of n, correct? This is called, the denominator is called the standard error, all right? So you get h bar minus 30. H bar is 28.76. You can get this value by using the calculator. You can also compute the value of s to get 12.2647. Is that all clear? Do you understand that?
Yes, sir.
Okay, and then you can get the value of z, which is minus 0.73. All right. Now you need to, in this case, you are using the approximate hypothesis testing, the hypothesis z test. So you use the standard number distribution to determine the value of the critical point. You can draw the graph here, and H1 is that m is less than 30, so you want to look at the left tail. The left tail is alpha, which is 5%, all right? It was given here. So alpha is 5%, that's why I have 5% here. And you can use the table of the standard number distributions to get the value minus 1.64, okay? And the value of z belongs to this region. This is called, there are certain regions. Therefore, we fail to reject the null hypothesis. If z belongs to the rejection region, then we can reject the null hypothesis. Do you understand?
Yes, sir.
Okay, which means that we don't have enough evidence to conclude that the specification has been met. So the answer is no for this. Okay, is that all clear?
Yes, it's clear.
All right. So if everybody, if you have any question, please feel free to stop me and ask question. Okay. This is just the solution you may get. Okay. Let's move on with the next case. I would say that is the 3' because it is not 4. I would say 3' because it is just a particular application of the third case. I suppose that all the x1, xn, they are independent. Okay, again, they are independent. They have the same distribution, and that distribution is the Rayleigh distribution. Okay, so I can say that its Hi can take the value 1 or 0 with probability P or Q equals 1 minus P. Okay, so you get this one, and I want to then I can find the mean of Xi. Let's say that is n, right? This in this case it is P, right? You can also find the variance of Xi, which is sigma squared that we learned, right? We use the notation x squared to denote the variance of Xi, sigma squared for this, and you get the variance of this particular distribution is P times Q. All right. Okay, P can be approximated by P hat, but we're not going to do that in this case. Well, in fact, under the assumption that, because we may have the assumption that we may assume that the null hypothesis is true, then you can get the fact that P equals P0. Okay, and then P becomes P0, or let's say Q becomes Q0. All right, then I can come up with the value. Oh, by the way, you can approximate P by P hat. Okay, which plays the role of H bar, and Q can be approximated by Q hat. Okay, which plays the role P hat Q hat. I'm sorry, P hat Q hat. So that plays the role of S squared. Okay, so if I get the value Z, which is X bar minus M0 over the square root of sigma square over n, then I can get the P hat minus the P0 divided by the square root of P0 Q0, all right, over n. And that's why we come up with the following rule, decision rule, to perform the hypothesis testing on the proportion. Is it all clear? Is it okay? Is that all clear, everybody? Is it okay?
Yes, I think so.
Okay, good. All right, let's consider the following example. Natural cork in wine bottles is subject to deterioration, and as a result, wine in such bottles may experience contamination. An article reported that in a testing of commercial tyrannies, 16 of 91 bottles were considered spoiled to some extent by cork-associated characteristics. Thus, the data provides strong evidence for concluding that more than 15% of all such bottles are contaminated in this way. We assume that the significance level is 5%. Can you think about that for a minute? Oh, fail to reject. Okay, let's see. This is H1, and then you get M is less than is more than 15%. Okay, is that clear? And then you come up with the value of Z, which is the square root of, oh, not really. It is P hat minus 0.15 over the square root of 0.15 times 0.85 divided by n in this case is 91. Okay, and P has to have which is 16 over 91, and you can get the answer. All right, do you understand? And that's going to be 0.69. Okay, is that clear? Is it okay? All right, and then you have a look at this. M is greater than 15%, then you get this one, right? That is 5%, 5%, and this value Z is 1.64. Z belongs to this one, right? So we fail to reject the null hypothesis. Okay, that's all right. Understand? It is all clear. So this is what we just learned so far. This is what we just learned. We test the hypothesis, normal distribution, and if the distribution is normal and you don't know the variance, then the population variance, then you use the standard distribution. This is the exact test. Okay, exact Z test. Or if you don't know the population variance, then it is the exact T test. If the distribution is not normal, then you need the assumption that n is large, and then you can perform an approximate Z test. Do you understand? Is it all clear? It is okay?
Yes, teacher.
Okay. Hours they sleep each day, it was found that the sample mean is 7.5 hours. We already did this problem, correct? And you remember that we used Z test for this problem? Am I right? Is that clear? Is that clear?
Yes, sir.
Okay, now I want to change the question a little bit. I changed the question a little bit, and this is what we get. Okay, this is what we get. And the only difference is that we still we have something further. We get the sample standard deviation, which is 0.7. All right, together with the population standard deviation. Which method can I use in this case? Can I use Z test or T test? Can you tell me? Which one? t-test or
Can
z-test?
you repeat the question once again?
Should we use z-test or this? Can we use z-test or t-test in this case?
Wait.
Just like z-test or
Yeah.
test.
Where is the condition with the sample standard deviation and the population standard deviation?
This is the one. Let's say this is the case. Then which one do we need to use? What do you think?
I think it's z-test because we already have the population standard deviation.
We do have the sample standard deviation, I think. We have both. What do you think? Can I use t-test in this case?
Z-test, not t-test.
In fact, you can use both. You can use t-test and z-test. Okay. You can use z-test, of course, because you know the population standard deviation. You can also use t-test because with the sample standard deviation and the assumption of normality, you can use t-test. Correct? Both of them are exact tests. So which one should I use in this case? If you have two tests, two available tests, which one should I use? If you have two options, what is the better option?
I think that the z-test is the best option.
Why is that?
Because it will approximate it more accurately because it is the population standard deviation.
Well, not really. The point is that the two tests give you exact tests, right? The two tests give you exact tests. That's why both of them are exact tests. So both of them are accurate, in fact. I don't think it is about the accuracy. It is about the power of tests. Why is that? I think I remember. If you remember, then you will remember what I mentioned at the beginning of the chapter when I mentioned the beta. 1 minus beta is the power of test. That is the probability that you can reject the null hypothesis when it is false. Do you remember? If you have two tests, then you need to compare the power of test to make the conclusion, to know which one is better. Okay, and between the z-test and the t-test, z-test give you a better, the higher power of test. So it give you more power, more chance to reject the null hypothesis. By using the z-test, you have more chance to reject the null hypothesis. That's why it is better to use the z-test. Do you understand? Is that all clear? Is that okay?
Yes, it is.
Okay, so it is better to use the z-test. All right. Now I want to give you another example. A very similar, a similar problem. Okay, it is very similar to what we just did. Actually, it is the same thing. It is the first one is the same question. Okay, and if you remember, it is t-test, right? In this case, you have the assumption of normality, the distribution is normal, and you don't know the population's standard deviation. Instead, you know the sample standard deviation. So you can use t-test, correct? Now, I want to change the question a little bit. I want to change it a little bit. Let's say I get this. Okay. What do you think? I change a little bit, just a little deal. So instead of 20, I have 40. Okay. Can I use t-test for this problem? Can you use t-test for this? Tell me, please. Can you use t-test?
Yes, I think so.
Yes, you can use t-test, right? Because for the t-test, there is no requirement for the sample size. You can use t-test even if your sample size is only 5 or 10 or 20 or 100. It doesn't really matter, right? Okay. Can I use z-test? Can I use z-test?
Yes, I think so.
Why is that?
Because it assumes that the population distribution is normal and the sample size is 40. Is it considered is large enough?
Okay. Well, if you can, well, look, if you have the assumption that n is large enough, you use that fact, then you don't use the assumption that the distribution is normal. The point is that in this case, you don't know the sample standard deviation. I'm sorry, the population standard deviation, right? Sigma is a no, correct? Sigma is a no, so you cannot use this case. No, you cannot use the first case. If you want to use the first approach, then you need the assumption. You need to know the population standard deviation, but you don't know it. Okay, so you need to use this one. It is the approximate test. Okay, so you need the assumption that n is large enough. Do you understand? So in this case, in the second case, you don't use the assumption of normality. You don't use that. Instead, you use the assumption that n is large enough. Okay. The first method is an exact test. Unfortunately, the second one is an approximate test. Okay. Therefore, between these two tests, the first one is the better one. Do you understand? Is that clear?
Yeah, it's clear, sir.
Okay. The first method is better. Okay, this is the last example I want to mention. Okay, suppose that we have these two data sets. This is X, this is Y. Okay. Now, can you tell me the method that I can use to perform the test? on the hypothesis that m, the mean value, is greater than 1. Suppose that we have two data sets here. Can you tell me?
Teachers, I think that we can use t-test for x, but we cannot use any test for y.
That's true. That's true. That is correct. For the first case, the distribution is normal, right? So and you don't know the population standard deviation, so you can use t-test for this one. Okay. For the second case, the distribution is not normal, right? Therefore, you cannot use this one. No, because for this you need to know the distribution to know that the distribution is normal. So you cannot use the second case either. All right. For the third case, if you want to use the approximate z-test, you need the assumption that n is large enough, right? However, in this case, n is not large, n is only 10, and the distribution is heavily skewed. It is heavily skewed. That's why you need n to be really, really big. Even 30 is not big enough. I think it should be like hundreds to be able to use the central limit theorem. That's why you cannot use what we just learned. Well, there are in fact some methods that you can use to test on the hypothesis, but it is not the one we learn in the course. Okay, so so the answer is no, you cannot do it. All right. Well, it becomes really easy if I draw the graph for you, but just have a look at this. Suppose that you don't know the distribution, don't know it, right? But you just have a look at the graph here, the numbers here. Can you tell me if they are the same, if they are the same or different? Whether they look quite similar to each other, right? And you, well, based on these two numbers, you don't know which one you should use, correct? Okay, so you have to draw the graph because before you actually perform some hypothesis testing. Do you understand? Is that all clear, everybody? Is that all clear? Hello, is that all clear?
Yes, sir.
Okay. So we just finished this chapter about the hypothesis testing. Do you have any questions so far? Do you have any questions so far? Is there any question so far? If no, then let's have a break. After that, I will move to the review for the midterm exam. All right. Me. Hello. Okay, great. So for the midterm exam, you need to study the first chapter of probability, in which you learn the concept of events, disjoint events, and independent events. Okay, and then you learn the operators with some rules. You need to learn complement rule, addition rule, and product rule. Then you learn the total probability formula and the Bayes formula. Okay. For the next chapter, you learn the random variables. This is the one. You learn random variables with distribution. So for the distribution, you can learn the CDF, the PMF, and the PDF, right? The density function, Boltzmann function, and the cumulative distribution function. You also learn some characteristics, including the mean, the median, the variance, the standard deviation, and the interquartile range. All right, okay. For random vectors, you only need to study discrete random vectors, and then you need to know the concept of joint distribution and marginal distributions. All right, and you need to know how to find the mean, the variance, with all the probabilities with for the case of random vectors. Okay, and the last chapter you need to learn is about some special distributions, including the binomial distribution, Poisson distribution, continuous uniform distribution, exponential distribution, and normal distribution. Okay, and the last thing you need to know is the central limit theorem. Is that all clear, everybody? Is that all clear, everyone? May I move on?
Yeah, teachers.
Okay. So this is the first example. Please think about that for a minute. Then I can move on with that. All right. An electrical system consists of 3 components, and the reliability, which is the probability of working of each component, is shown in the figure. Assume that the components work independently. Find the probability that the entire system works. And then if the entire system works, what is the probability that component A works properly? Can you think about that for a minute? Then I will go over the solution. All right. Well, let's say this is D, right? And this is C. Suppose that A, the events that the entire system works. Then A is simply D and C, correct? So you want to find the, in question A, you want to find the probability of A, which is the probability of DC, all right? That's all clear. And this is the probability, oops. This is the probability of, this is the probability of D times the probability of C, and that is going to be, what is the probability of D? The probability of D is something that you need to know, right? You need to compare. And the probability of C is 80%, right? It is 0.8. Now you need to find the probability of D. And the probability of D is simply, what is that? The probability of D is the probability of A or B, correct? Okay, this is what you need to know. Then you use the addition rule to get the probability of A plus the probability of B minus the joint probability AB. Do you understand? Okay. So you come up with the probability of AB, which is that? It is the probability of A times the probability of B. The probability of A is 0.9. The probability of B is 0.7, so you get 0.9 plus 0.7 minus the product. Do you understand? Okay. So you get the value probability of D equals 0.97. Is that all clear, everybody? Is that all right? Good. Okay. So as long as you know the probability of D, you can play back into this expression to get 0.97 times 0.8. That will give you the final answer. That's all right? Okay. Do you understand? Okay, all right. Next, you can also find the probability of D by using the product rule instead of the addition rule. So I get the probability of D bar, the complement. That is one. That is the probability that that A doesn't work or and B doesn't work. Right? D is the first part. So this becomes A or B. I'm sorry, A and B, A bar and B bar. So you get the probability of A bar times the probability of B bar. Well, the probability of A bar is the probability that A doesn't work, and that is 1 minus 0.9. So you get 0.1 for the first component, the first factor. For the second factor, you get 0.3, which is 1 minus 0.7. So you get 0.03 for the probability of D bar. And then I use the complement rule to get the probability of D, which is 1 minus the probability of D bar. And then you get 0.97. Do you understand that, everybody? Okay, so you can use this approach or the other approach to get the probability of D. The point is that if there are two events, either way is fine. But if you want to generalize the problem with more events here, more components, then there are more events. And then if you use the addition rule for many events, the follow will be much more complicated. Therefore, I suggest you to use the second approach, which is much easier. Okay, is that all clear? Is that all clear? Is it okay, everybody? Good. All right. Now let's go back to question B. We continue with question B. For question B, I want to find the conditional probability of A given E. What is that? What is this probability? What do you think? In order to find the conditional probability of A given E, you need to use the base formula. That is the conditional probability of A given A times the probability of A divided by the probability of A. We already knew the probability of A, right? It is this product. You knew that. You also know the probability of A, which is 0.9, I think. So it is remaining to find the conditional probability of A given A. Well, what is A? A is this one. So if you know that A works properly, then the first part works properly, correct? Therefore, you only need to guarantee that the second part works properly to make sure that the entire system works, correct? So I get the probability of C given A, and because A and C are independent, you can drop the condition A without any problem. So I get the probability of C, okay, which is 0.8. Understand? Now I can find the conditional probability of A given A, and then I can get the conditional probability of A given A. It is not 1, obviously. Do you understand? Is that all clear? Is this all right, everybody? May I move on?
Yes, teacher.
Okay, great. If you have any problem, please feel free to tell me. If you want me to slow down a little bit, that is fine too. Just if you have any problem with class, please let me know immediately. The second problem is this: a certain federal agency employs 3 consulting firms with probability 35%, 40%, and 25% respectively. From past experience, it is known that the probabilities of cost overruns for the firms are 5%, 25%, and 15%. What is the probability of cost overrun? The second question: suppose a cost overrun is experienced by the agency. What is the probability that the consulting firm involved is company C? All right. Then, okay, in question C, we do a similar question, but we change a little bit. In that case, the assumption is that a cost overrun is not experienced by the agency. Okay. Can you think about that for a minute, and then I will go over the solution. All right. In order to solve the problem, we need to see that you want to find the probability of cost overrun. Let's say that is R, and ABC are for the 3 companies. Then I get A. I need to draw the probability tree A, B, and C. Okay, with R here, and then R bar. All right, and then R, and then R bar, and then R and R bar. Okay. The probability of A, the probability that the company A is involved is 5%, no, 35%. Okay, that's 0.4, and you get 0.25. All right. For A, if A is involved, then the probability of cost overrun is 5%, 0.05, and then you get 0.25. Oops. And then you get 15%. So you can find question A. You can find the probability of cost overrun. What is that? That is the probability of A times the probability of R given A plus the probability of B times the probability of R given B plus the probability of C times R given C. Do you understand? And then you get, for A, you get 35% times 0.05 plus 0.4 times 0.25 plus 0.25 times 0.15. Do you understand? That's all right. Okay, that is question 1. Question A. For B, how can we get B? You want to find the probability that the consulting firm involved is company C. The consulting firm is C, so you want to find the probability of C if you observe a cost overrun. So let's say given R. It is natural to think about the base formula. So you get R given C times the probability of C over the probability of R. The denominator is the result you obtained in the first question. For the numerator, it is simply the last term of the sum here, and then you can get the answer. Understand? It is all right, everybody? That is clear, correct?
Yes, teachers.
Okay. Yep. Thank you. For question C, you want to find the probability of C given R because you observe no cost overrun. So you get this probability, and that is the conditional probability of R given C times the probability of C over the probability of R. Okay. Probability of C is given, right? That is 0.25. For the probability of R given C, it is 85% here, right? You get 15% for R and 85% for R. If the company seed is involved, so you get 0.85 for this factor. For the denominator, you get the probability of R, which is 1 minus the probability of R, and you already knew that probability in the first question, in question A, so you can find this probability by using the complement rule, and then you can get the denominator of this fashion, so you can get the desired value. Do you understand? Is this all right, everybody? Is it okay? Okay, if you have no question, please feel free if you want me to slow down or you want me to give more explanation, all right? This is question C, question 3, on deciding computing